You know how sometimes in life the answer isn't just one specific number, like maybe you're trying to stay under budget or keep your thermostat in a certain zone,
Yeah.
or even just thinking about speed limits. You're not after one exact value, but a whole like range of what's okay.
Exactly. And that's really where this math you brought us today shines. We're diving into linear inequations. They're like equations close cousins, but with a key difference.
Right. So our mission for this deep dive is to sort of unpack the main ideas behind these inequalities, get the rules straight for solving them, and importantly, figure out how to actually picture the answers, especially on a number line, based on the material you sent over.
Okay, so let's start with the basics. An equation, everyone's probably pretty familiar with that. It's a statement saying two things are equal, like 6, 5 divised, simple.
Hmm.
Or maybe $2 plus 1 equals 71. You find the specific value that makes it true.
Right, like finding that one point. But in equations, they use different connecting verbs, as your source calls them. So instead of just equals, you've got,
You've got less than, greater than, and then the ones that include the edge case, less than or equal to, and you, greater than or equal to. These basically say one side isn't necessarily equal to the other, but, it relates in a specific way, smaller, bigger, or possibly equal. Think 6 10s or maybe an $8 there.
Okay, and your sources bring up two really important ideas here,
Yeah.
the replacement set and the solution set. What's the difference?
Good question. So the replacement set is kind of like the big pool of numbers you're allowed to pick from for your variable. Is it natural numbers only, or maybe integers, which includes negatives and 0, or all real numbers? This set is, well, it's fundamental because it sets the boundaries of what's even possible.
And the solution set, then?
That's the group of numbers from that replacement set that actually make your inequation statement true. Your test yourself section had a good example. If you're looking at $6, but your replacement set is just $2, $4, and $6, 8,010. Well, only 8 and 10 from that list are actually greater than 6. So 8, 10 becomes your solution set.
Ah, okay. So the replacement set can really narrow down the final answer. What about solving them, though? Like if I have 3 by 5 10 digital dollars, are the rules the same as for equations? Adding things, moving terms around.
Mostly, yeah. They feel pretty similar at first. Add the same number to both sides. Inequality sign stays put, subtract. Same deal. Even multiplying or dividing by a positive number, no change to the sign. It works just like you'd expect with an equation.
Okay, that sounds straightforward enough.
Yeah.
So where's the catch?
Yeah, here it is. This is the big one. The rule that often trips people up. If you multiply or divide both sides of an equation by a negative number, you absolutely must flip the inequality sign.
Flip it. You mean like less than becomes greater than? Or vice versa?
Exactly that. Your source material gives that perfect example. 80s, 8s began to 6, 46. To get $6 by itself, you need to divide by medic 8. And since Montebex is negative, boom, that's to flip to. So 8 is commands of 4, 4 turns into 6 frac 4, which then simplifies down to 6 4 1. It's like the negative multiplication reverses the direction on the number line, so the inequality itself has to reverse too.
Wow, okay. That one rule seems super important to remember. So once you've solved it, and you have your solution, like 6 frac 1, 2. How do you show that visually? Especially if it's a whole range.
Yeah, that's where the number line is so useful. Just a straight line with numbers marked on it gives you a really clear picture of the solution set.
And how it looks depends on the type of numbers in your replacement set, right?
Yeah.
And the inequality symbol.
Precisely. If your replacement set is discrete, like natural numbers, 1, 2, 3, or integers, -1, 0, 1, then your solution is just shown as thick dots on the specific numbers that work. Like if you had 6 by 4 and $6 had to be a natural number, you just put dots on 1, 2, and 3. That's it.
Okay, simple enough. But what if the replacement set is real numbers? Including fractions, decimals, everything.
Right. Then you can't use dots because there are infinitely many numbers in between. So you use a continuous line segment or array, and the endpoint, the boundary number, gets marked differently. If the number is included, like with a or a, you use a solid dark circle. Shows that point is part of the solution.
And if the boundary number isn't included, like 4 or down,
Then you use a hollow circle, an open circle, at that number. It means you get infinitely close, but don't actually include that specific value. And if the solution goes on forever in one direction, like 6 by $4, you draw a dark arrow pointing that way. Your source's number line section and that exercise 21B show these differences really well. The dark versus hollow circles and the arrows.
yeah, seeing it laid out like that, it makes the idea of intervals really clear, not just single points. So thinking about that, this whole idea of a range or a boundary, why is understanding this stuff in equations actually useful for you, the listener? How could knowing about these limits or possibilities help when you're looking at data or just, making decisions?
It's a great question. It really is about how we define acceptable ranges, not just exact targets. So we've kind of journeyed from what inequations are, how they differ from equations, through the rules for solving them, especially that tricky negative flip, all the way to visualizing these solution sets on a number line with dots, circles, and arrows.
It's pretty cool how defining limits works mathematically.
It really is. And maybe here's a final thought to leave you with. Think about all the limits and boundaries in the real world. Speed limits, yes, but also budget constraints, maybe safe operating temperatures for equipment, even recommended daily amounts of vitamins or something. How is the fundamental logic of these inequations sort of working behind the scenes, quietly defining the solution, sets the acceptable zones for our actions and choices every day?
That's a fantastic point to ponder. Thanks so much for bringing this topic in for a deep dive.